Hello AP Chemistry and welcome to the first video for Chapter 20. So we're going to first talk a little bit, a really brief review about redox. Most of you will probably need to go back and review your rules for calculating oxidation states because obviously that's a key thing before we can talk about anything else. So make sure you review that. Alright, so what is oxidation? That's not where the line was supposed to go. Oxidation, right? This is when we lose electrons, right? And what that means is that we become more positive, right? Right. Reduction means we gain electrons, which the end result is that we become more negative. Right, or become less positive. Now here it's really, really important, right? So become more positive doesn't even mean it has to become positive, right? If we go from -2 to -1, that becomes more positive, right? Likewise, down here, if we go from -2 to -6, that becomes more negative, yes? All right. So then, okay, so anyway, that's a quick review of redox. Now, here, we're going to sort of build on that. So we talked, I guess, earlier this school year about how balancing redox reactions is not as simple as just putting coefficients to balance our species, right? And here is where that kind of comes in, all right? So this is a table of standard reduction potentials, okay? Meaning that every one of these reactions is written as a reduction. So if we look, right, these are all reductions. Right? See F2, which would be 0 to -1, right? Permanganate ion to just the manganese ion, right? 0 again to -1, right? All the way down to here where we have metals that go from their ions to their solids, right? So this is a standard reduction potentials table. Now, this is from table 20.1 from your chapter. Note that Appendix E in your textbook is also a more thorough version of this, okay? There is no expectation, kind of like with your free energy values or your standard heats of formation, there's no expectation that you memorize all of these, but you should know how to use them when you're given them, okay? So for example, we'll see here, there's a couple of things. Each standard reduction, right, is accompanied by a voltage, okay? This is the electromotive force, also known as your E value, also known as your voltage, right? And things to be mindful about, right, are that we see that some of these are positive values. We have a 0 because this is our standard by which everything else is measured. And then we have our negative values, okay? Positive values, so all of these positive values, right, are thermodynamically favorable, right? Positive values are favorable. That means they tend to happen spontaneously without outside help, okay? That means negative means unfavorable and don't happen to happen with outside help, which should really, really make sense, right? Because if we think about it, if we come down here, right, lithium, right? Lithium ions turning into lithium solid, right? Is that something that happens spontaneously in nature? No, the opposite, right? We know that lithium is never found alone in nature. It's always found, right? Same with all of our group 1s, right? It's always found as part of a compound, meaning it's always found as lithium ions in nature, right? Which makes sense because that means then if we flip this, just like going back to all the thermodynamics we've talked about this year, if we flip this reaction and talked about, for example, lithium solid going to lithium plus an electron, that value would have a positive 3.05, yes? So the oxidation of lithium, very favorable, okay? So then, another way to interpret this, right, is that this top part of the table, right, these are things that are very easily reduced, okay? Things down here, very easily oxidized if we're going from the product side, okay? So there's a lot of information that's tucked into this table. Another quick thing that you should note, right, is that voltage, right, when we're talking about voltage, 1 volt is equal to 1 joule per coulomb, okay? And that's the unit relationship here, right? So something to take note of, right, is that volts are an intensive property, all right? Meaning that even if I scaled this reaction up to 2F2, 4 electrons, and then 4 F minus, right, this voltage doesn't change, because voltage is based on the amount of energy basically relative to the charge, right? The amount of energy relative to the change in charge. This is this is a coulomb, not a charge, but joules per coulomb, if that helps, right? But what happens is that this goes up and this goes up, which means that this stays the same, okay? Volts, uniquely intensive in terms of properties. And the last thing to point out is that, yes, these do balance our electrons, right? So meaning that this tells me how many electrons are here, right? Or how many electrons are here, for example, as part of my reduction half reaction, okay? All right, so let's go ahead and practice using this table a little bit. So, given some standard reduction potentials, how we actually balance a redox reaction. So one, kind of like we just talked about in the acid-base chapter, we need to ID whatever's present so we can figure out what's going to participate in the redox reaction. Then we'll arrange our half reactions correctly, balance our electrons, and then sum them. So here we have zinc in aqueous copper 2 sulfate, right? So CuSO4, right? And we know that, hypothetically this is going to make CZnSO4, right? Probably aqueous and some copper, okay? Now, identifying my reactive species present. So here I know I have some zinc solid, I know I have some copper ions, and I know I have some sulfate ions. Those are my options, right? I also have water. Let's not forget about water. So, thinking about what we know, right? If we look here, if we look at this balance reaction, right, we already know that zinc would go from 0 to +2, right? And we know that copper would go from +2 to 0, right? And this is a pretty easy one. So when we go back and look at our table, right, that's what we're going to be looking for. So let's go look for copper. Okay, so this one has copper, and it has it written in the direction that we need, right? Copper 2 plus 2 electrons gives us copper solid. Okay, so Cu2 plus 2 electrons gives us copper solid, right? And this has a value of plus 0.34 volts. All right. Next up, we know we have zinc. So let's go find zinc. This reaction contains zinc. What do we notice though? Right, we actually need the backwards version, right? We need zinc solid gives us zinc 2 plus 2 electrons, which means that we're just going to flip this value. So plus 0.76. So now we have our half reactions arranged correctly. We're going to balance the number of electrons. Turns out that this one has 2, this one has 2, so no scaling is necessary. If these didn't match, then we would have to do some scaling until they both had the same number of electrons. And then we're going to sum this up, right? So we see that this cancels, right? And so Cu2 plus zinc solid gives us Zn2 plus Cu solid. And then we would sum these up also, right? And we'd have our 0, our 1, 1.10 volts is my E value, okay? So 1, we already have a net, which is kind of convenient. And 2, we have a positive value over here, right? So again, going back to what we said on the first page, yes, a positive value means this happens spontaneously, which means that when I put a piece of solid zinc into a solution of copper sulfate, right, the oxidation reaction occurs, right? Meaning that we get the transfer of electrons, right, from the zinc to the copper, right, and we end up with copper ions in solution, right? Which is why we see, right, visible evidence of reaction occurring, right? We see that we are depleting my copper ions due to the less blue hue of the solution, right, and the solid forming on the surface. Now, thinking about that from another point of view, what happens if I put copper solid in a solution of zinc sulfate? Right, no reaction, right? Because if we go back here, if this reaction has a positive voltage in the forward direction, if I wanted to reverse this, it would have a ding, 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 negative voltage, meaning that this reaction does not occur. Okay? All right. More practice. All right, let's say that we have some zinc in an aqueous solution of sodium chloride. Right? And then so we know that we would probably form this and some of that, right? Single displacement reaction. Now, let's go ahead and take a look at our table, right? Here we have zinc going from a 0 to a +2, And here we have sodium going from +1 to 0, right? Okay, so let's go find our pieces. All right, so zinc again is going to be plus 0.76. So we have Zn. All right, and so next up we have to go find my sodium. And sodium is down here. So sodium plus to sodium solid is negative 2.71. All right, so here in order to scale this, right, so we would take this and we'd multiply it by 2, right? Bearing in mind that, again, voltage, intensive, doesn't matter how much of the reaction is happening, okay? So then here, this would tell us that we have our 2Na plus zinc solid is going to give us zinc 2 plus Na solid. And then what do we have over here? Right, we're going to have a negative voltage value, right? Meaning that, right, this reaction does not occur in this direction. Which means that if I were to put a piece of zinc in a saltwater solution, I would not make solid sodium, right? And that should make sense because we know, right, that solid sodium is going to more readily go this way. So even if we did produce solid sodium, right, it would immediately go back in this direction, right? Kind of like how we talked about with strong acids and strong bases, they dissociate completely, have no tendency to go in the backwards direction, right? Likewise here, this only goes, right, in this direction. So this reaction is actually no reaction. All right, next up. Let's say we have some sodium in water, right? So my species are going to be sodium and water. And hopefully you remember what this makes. Right. This makes NaOH plus H2. So let's go look for my species, right? Well, let's go look at my redox, right? I know that this is 0 here. This is +1 here. So let's go back here. Sodium to sodium plus. And then if we go back, we need to find something that has to do with water, right? And so let's be specific here. Water as a reactant, right? And water over here, right? And so what's the relationship here we're looking for? Right. So we're looking for water as it relates to hydrogen. So if we go back to our table, let's look for water on either the reactant or the product side, right? So here's one that has water. And here's another one that has water. And here's another one that has water. Okay. So then we have to look for the one that is pertinent, again, relative to what we're talking about. So we are talking about water producing some hydrogen gas, right, and hydroxide, and this is actually exactly what we're looking for. So we would have 2H2O plus 2 electrons. Gives us H2 and 2OH. And this one has a value of negative 0.83. So we would take this and multiply it by 2, right? And this gives us 2Na, right, solid, plus 2H2O gives us 2Na plus H2 plus 2OH minus, right? Which then, right, that is the net for what that process happens up there, right? And then over here, right, we do end up with a positive voltage, which means that, yes, this happens, which should make sense because this is one of those reactions we've been talking about since sophomore year, right? Group 1 metal plus water gives us hydrogen gas, right, and a metal hydroxide, right? Positive voltage, it does happen. If I wanted to do copper and water, right, so we already have the water part, so 2H2O plus 2 electrons gives us H2 plus 2OH minus, right? So then we just have to find the copper, right? So if we're going to take Cu plus H2O, And let's see if it does the same thing, right? So Cu probably 2 plus that, right? And so let's see if this is a possibility. So if we go back here and we find copper, here we go. So copper solid to copper 2 plus is 0.34. Flipped. Copper solid. Oh. All right, so if we look at this, what's our voltage? Right, negative overall voltage, which means doesn't happen, right? Which is why, looking over here, right, we use copper for water purposes, right? We may have copper tubing for water, right? Some drinking vessels are made with copper, right? But copper is something that is inert to water, okay? Here though, right, so here's the video of sodium metal and water, which should be familiar, right? So we put sodium metal in water, and then we see that there's a reaction, we see evidence of gas formation, right? And then we see that it's decidedly exothermic, right? And that's why we get the flame part, because that's the hydrogen catching on fire, courtesy of the exothermic nature, right? So, again, very, very different than copper and water. Okay. Thank you for listening. Be good, and I will see you soon. Bye.